So in today's video, I am going to discuss in detail about selective harmonic elimination, which is a modulation method used in especially in MMC HVDC system. All right. So as per the theory, there are different modulation schemes that are available. So let me discuss. So, as per the theory, the modulation strategies can be divided according to the switching frequency, the fundamental switching frequency techniques, and the high switching frequency techniques. So, when it comes to MMC HVDC system, we normally prefer those control methods or the PWM methods which are fundamental switching frequency operated. Such methods are nearest level modulation, selective harmonic elimination, etc. Because why we are interested in fundamental switching frequency? It is because we have a huge number of submodules, maybe in hundreds, uh, when it comes to HVDC system. So, in such a system where the number of submodules, let's say half bridge submodules, so each half bridge submodules contain two switches, so the number of switches are more. If we operate those switches to a higher frequency, our switching losses will be high. So to avoid that, we prefer those techniques which has fundamental switching frequency. So in my previous videos, I have discussed in detail about different control techniques such as nearest level modulation or such as space vector. Now in this video, I am going to discuss about the selective harmonic elimination. So the NLM, we know that the NLM is just rounding the reference waveform according to the number of submodules, right? So this is the nearest level modulation, and it is it is one of the favorite you know modulation scheme that is used in the HVDC system. Apart from this, selective harmonic elimination. So what is selective harmonic elimination? The selective harmonic elimination method is called the fundamental switching frequency method, based on the harmonic elimination theory proposed by this. A typical level multi-level converter output with the fundamental switching frequency scheme is shown. Now what happens is that in selective harmonic elimination, as name suggests, we eliminate certain harmonics. Those harmonics could be odd harmonics, triplet harmonics, and so on. And those are very dangerous for the system. So we develop these techniques in a way that it should, eliminate those harmonics which are selective, which are our own purpose. So this is the main idea behind the selective harmonic elimination, and it can be implemented via Fourier series expansion, where we need to determine uh, the components that we want to eliminate, and for those we need to select the conduction angles, the thetas, so that those particular according to the reference waveform, those particular harmonics should be eliminated. And for that we normally have table uh, that is followed when uh, when our reference waveform operated. Normally, the the angles also depends upon the modulation index MA. So if the MA changes, the modulation index changes, the angles are also changed accordingly, right? So this is what is explained in this article. So pre-calculated switching angles are stored as in data memory or the lookup table. So that was lookup table. So our controller can decide that based on the modulation index that which particular angles to be selected for the you know harmonic elimination. And these are the high switching frequency techniques. We have a carrier level shifted PWM, right? This is SPWM, this is THPWM, and this is SPWM, right? Carrier phase shifted. All right, so let me go through this PPT. That's a small PPT. Now in this PPT, basic MMC architecture is explained. That how basically the system that I'm going to show you is developed. It has 8 submodules in either arm, and it is made up of half bridges. So this is a major comparison between very famous control techniques such as the SPW and the sinusoidal PWM technique. It is a sinusoidal reference. It is a triangular carrier, right? And it has a very high switching frequency, so large switching losses. So this is normally avoided when it comes to the HVDC system, whereas its implementation is very simple. Now compared to come to the space vector PWM, it uses an alpha beta stationary frame reference, selects adjacent active plus zero voltage vectors, better DC utilization compared to the sinusoidal PWM, 15% more. That's the advantage. Dwell times calculated per switching cycle, complex for multi-level but scalable with algorithms. So when it comes to the high number of submodules, the space vector becomes very complex. Whereas in NLM is the favorite. It's the easily scalable, and but when it's come to low number of submodules, such as in our case 8 or less than 8, this gives very poor harmonic distortion. Excellent for high number of submodules, yes. And last but not the least is selective harmonic elimination. So the selective harmonic elimination, we need to compute the switching angles from Fourier analysis. It eliminates specific low order harmonics such as triplet harmonics or fifth or seventh or order harmonics, and very low switching frequency. This is one of the advantage. So we have a very minimal or the minimal switching losses, and it requires of the transcendental equations lookup table implementation for real time control. Yes, so it is time taking, but for the for a system where the number of submodules are low or the number of switches are low, this can be a good choice, the selective harmonic elimination. So as per the theory, we have a Fourier series of a step waveform, right? So in the first quarter, the switching angles are these based on this equation, and to eliminate the harmonic order of H, we need to follow this. And for 8 submodels eliminating, so H could be 5, 7, 11, 13, 17, 19, 23. So basically there are 8 equations and 8 unknowns. So if we solve via any iterative methods such as Newton-Raphson or Gauss-Seidel, we can find that these are the switching angles in the lookup table, and I have implemented here in the MATLAB as well. So I'll show you that how I have done this. So as I told you that if the modulation index changes, you need to change those alpha angles. So if your modulation index is greater than 0.95 or equal to, you need to you basically need to follow these switching angles. If you have a m that is equal to or greater than zero point 0.9, you need to follow this. So basically selective harmonic elimination is modulation index dependent. If you don't follow, then the result would be different for the different if we keep the same angles for different modulation index, then our result will be, you know, unexpected. So this is the implementation. We need to use the clock transformation so that we can get alpha beta components. So for that we should have a reference voltage ABC in the form of ABC. Then we need to calculate the alpha and the beta terms. In the second step, from the alpha and the beta terms, we need to find the angles using A10 function. This gives the instantaneous phase angles of the rotating reference vector in the stationary frame. Right, in the step 3, we need to find the modulation index using this formula. M is equal to V alpha square plus V beta square, and take its square root, and we need to scale down the modulation index so that it should not exceed the limits, right, from 0 to 1. And then we need to select the SHE English selective harmonic elimination angle, right. So a table is implemented in the MATLAB. This is the overall signal flow. You have an input signal, you convert then into the alpha beta terms, then from there you find the angles and the modulation index, then you give it to the, selective harmonic elimination method, where normalized level is -1 to +1. Then based on this, the particular, signals are generated and used depending upon this waveform. So this is the expected output, SHE output. We are using the 8 submodules, right? So as per the harmonic spectrum, what we expect is the very low for frequency harmonics compared to the SHE. So as you increase the, frequency or moves on, and the lower, harmonics, the higher order harmonics are very low compared to the SPWM. So these are some advantages of the SHE. Fifth and seventh harmonics near zero. 11th and 13th harmonics eliminated. Fundamental preserved at target M. Only 8 switches per cycle, and switches loss are reduced compared to the other PWM methods. 70% less. This is the SPWM comparison. So these are the limitations such as high switching frequency. As I told you that SPWM is not used due to the high switching frequency. High switching frequency means high losses, and complex carrier synchronization for 8 submodules. Electromagnetic interference issues at high frequency. This is one of the issue. And filter size and cost are, increases. There increases. Space vector. So no need to explain the space vector here. This is the NLM. I have already explained it. And so this is the overall comparison between the different PWM methods. So we'll focus on SHE. So the switching frequency is fundamental, whereas NLM is fundamental, and space vector SPWM has high switching frequency. Switching losses are high in SPWM and space vector. NLM is very low. This is also very low. THD is very low in SHE, 3 to 8%. Fifth and seventh harmonics are present, reduced, present, and eliminated. They are eliminated. Harmonic control is precise, whereas in NLM there is no harmonic control. DC bus utilization is 86%, 100%, 100%, and 90%. Implementation is moderate. Real-time compute is low. Lookup table, using the lookup table. Offline design is required. Yes. Capacitor voltage balancing sorting needed. And transient response is fair. Filter size should be small because the THD is already reduced, and best for the system having the lower submodules. So this is the comparison in the form of THD and the switching losses. So the switching losses, you can see that in the form of SHE is very low. And this is the overall Simulink implementation of this. We have a three-phase VABC reference. Then we use the clock transformation so that we get alpha and beta terms. So from the alpha and beta terms, we extract the angles, and we found the modulation index. From there, we formulated a lookup table, right, based on the modulation index. And from this, using the angles, we basically calculate and move on the switching level. From there, we have different offsets and SHE waveform for each phase. Then this gives a signal, and these signals finally goes into the capacitor and sorting algorithm. So this is a capacitor voltage balancing algorithm. And after that, we using, since we have 8 submodules, so with this we have a 48 IGBT drive signals for our overall system. And this is the conclusion, overall conclusion of this work. So let me show you the model. So this is the overall model. We have 8 submodules in either arms, in upper arm and as well as in lower arm. We are measuring the voltages. We are measuring the arm currents, and those arm currents and the voltages are sent towards the controller. And on the left side, we receive the signals, and these signals are the basically the switching signals. So each port contain 8 switches, 8 signals, and these signals are using the NOT gate. These signals are sent to these universal bridges. So here, this is the control system. In the control system, you can see that the power reference, grid voltage, reactive power reference, line current goes into this block. So this blocks control the active and reactive power using the conventional theory. And this conventional theory is based on the VD, VQ, ID, AQ terms, where cross coupling is there. And finally, you can see that the reference voltages goes out, and there they comes in here. This is the reference so that we can calculate the theta and the alpha terms. You can see that for the theta we have a single value, but for the alpha we have 8 different angles, and here inside we basically calculate the different uh, lookup tables. Here you can see this is the modulating signal that comes out after the switch level, and we can open this and we can basically see that this is a waveform from 0 to 8, because we have 8 submodules, right? And these signals goes into this voltage balancing algorithm where they control the overall uh, you know submodule voltage balancing and all that is happening here. So you can see this, that first of all we are converting the our signals into the alpha and the beta, and we are extracting the theta as well using the alpha and the beta. Then we have different limitations and angles, and you can see that we have formulated a lookup table based on this. So if the m is greater than or equal to 0.95, we have this condition. If m is greater than 0.99, we have these angles. If m is greater than or equal to 0.85, we have these angles, right? So on and so forth. So this is all about the selective harmonic elimination. Let me show you some results. So you can see that our capacitor voltages are very well balanced, right? And I can show you different waveforms, such as the voltage waveform, quite clear, right? And there are some grid measurements and the circulating current measurements as well. So this is all about this. If you have any question, you can simply ask me. Thank you for your time.